subtopic in simple harmonic motion. It is about vertical mass and spring and the simple pendulum. Okay. So before this, I always show the example about the spring which is in horizontal plane. Now the position of the mass and the position of the spring is vertical. Okay, so from here, look at here. This is these three, okay, is the same spring. Actually, this A, B, and C is the same spring, which different in condition. Okay, for A, the spring is in relaxed position. Relaxed position means when there is no load at the end of this spring. The spring is hung, okay, fixed from the, for example, from the retort stand, okay, and there is no load at the end here. So this is the spring in relaxed position. Relaxed position means position in vertical position. Okay, and then for B, when the load is attached to the spring, it will extend, okay, with a displacement D here. For example, I label here with D. So it will static in this condition. Okay, when it is stable, it will static. So here we call it the spring here is in equilibrium position in Y position. Okay. And then C is the spring. When someone pull, for example, when someone pull it down and then release it, it will move up and down. For example, here it's moving up with Y from the equilibrium position with a Y displacement. Okay, have a look at one by one. So here, this line, this dotted line here is the equilibrium position. Okay. When the mass and spring at equilibrium position, okay, here is remember when the object in equilibrium condition, the net force. Remember we learn it in equilibrium. The net force is equal to 0. Remember this one? Net force is equal to 0. So here when we label this one, okay, when I label it, this is B. Okay, at this part, at equilibrium position, the net force is equal to 0. So net force here, the external force here is the forces that act on this system. One is, this is mg, mass of load, and then another one is this one, restoring force. This is, we call it restoring force. So Fr, so I explained it in our first lesson about simple harmonic motion about restoring force. What is restoring force? Restoring force is always directed opposite in the direction of the displacement. Now the displacement is downward, so the restoring force, the direction is upward. So the restoring force is actually in Hooke's law. Remember Hooke's law? F is equal to minus kx. This is Hooke's law. Okay, so this is the restoring force. Okay. So in this example, in this position, okay, in equilibrium position, okay, so I will write the equation here. The net force is equal to 0. So here Fr directed upward minus mg is equal to 0. So here, FR. Okay, FR. So I will substitute FR. Look at Hooke's law. F is equal to minus Kx. Okay. Okay. Now I just take the magnitude. Okay. I erase the minus first. Okay. F is equal to Kx. This is Hooke's law. So here, F here is the restoring force. Same with this one. The restoring force. The restoring force is equal to, for this case, the restoring force is equal to K and then X. What is the value of X here? So it displays from the relaxed position to the equilibrium position with distance D. So I put here D. Alright. So I will substitute this FR inside this equation. So FR here becomes KD minus mg is equal to 0. Oh, no, kg, kd. So from here you will get one relation. Kd is equal to mg. This is the relation when the object is at equilibrium position. Kd is equal to mg. So from here, okay, you can find the value of K, the spring constant, by using this relation. This relation is from the equilibrium condition equation, the first condition of equilibrium. Net force is equal to 0. So by using this concept, equilibrium concept, okay, Fr directed upward minus mg downward is equal to 0. So Fr here is equal to Kd. Why do you write Kd? Kd here is from the Hooke's law. Kx. X here substitute with D because the mass displaced with D. The spring is displaced by the displacement D. So replace X here with D. So from here you can get one relation. Kd is equal to mg. Okay, this equation is only for the object in equilibrium. Okay. What about the object when the object is displaced up and down, up and down? For example, here the object is up, above the equilibrium position. Okay. So for this one, if you want to find here, okay, at this point. At this point, this is mg. Okay, and then again this is the restoring force. Okay, by using Hooke's law, okay, F is equal to minus Kx. From Hooke's law, F is equal to minus Kx. Okay, so here minus Kx. What is the value of X here for this object? Okay, the value of X here is okay, this is the relaxed position of the spring, and then this is the displacement when the object is displaced. So here, from here to here is the value of X. So here, to get the value here is D minus Y. Okay, so here is D minus Y. So I put here X, I replace it with D minus Y. Okay, so okay, here Kx minus mg. So here is minus mg. Okay, F here, for this one, the net force is not equal to 0 like it is in equilibrium position. But for this one, F is equal to minus Kx, okay, restoring force minus mg. Okay, so the value of, there's a value of F here. Okay, so here when you expand it, it become minus Kd, not Kg, Kd. Here I erase first the minus sign here. Okay, okay. So F is equal to Kx minus mg for this position. This is Kx minus mg. Okay, and then x here I replace with the displacement. Displacement is from the relaxed position to the displaced position. So here it becomes Kd minus Ky minus mg. So look at here. Kd is equal to mg. So I put here mg minus Ky minus mg. So mg 0. So the equation here become Ky. So here F is equal to Ky minus Ky. This is for the displaced object. This one. So here it's easier for you to see that. If you want to find the force here, the restoring force, the value of the restoring force here, you just take the displacement is from the equilibrium position to the displaced position. So from the equilibrium position to the displaced position, the displacement is y. So you can calculate by using this equation. This is actually Hooke's law. Okay, so y here is the displacement. This is the displacement from the equilibrium position. Okay, so that is about vertical mass and spring. And then another one is about simple pendulum. Okay, for the simple pendulum, I'm not going to explain details about simple pendulum. Here, I just want to tell you the value of angular frequency. Before this, in spring, the angular frequency can be calculated by using this equation. Omega is equal to Z K over M. This is only for spring, valid only for spring. But for pendulum, if you want to find the angular frequency, you can use this equation. Z G over L. Okay, where L here is the length of the string. Okay, G is the gravitational acceleration. So you can use this equation to find the angular frequency for simple pendulum. Okay, that's all for now. Finish about simple harmonic motion. Thank you for watching. Assalamualaikum.